Just to check, do you know the Taylor Swift song, Antihero? It's me, hi. It's me, hi. I'm the speaker now. That's how I pronounce my name. Okay, so let's begin. This is going to be a talk about AI. And in order to not always say AI every time, I'm going to also say ML. I know that they are not exactly the same thing, so ML is a subset of AI. But just for the purposes of this talk, suppose that they're approximately the same. So when I say AI, when I say ML, we always think about machine learning with neural networks and so on. The other thing that we have to concern about is traditional software, or software that doesn't use AI. So we have these two words. They have some stuff in common and some stuff that is different. And we will see that we can focus a lot on the stuff that is in common in order to do security for AI. So what is at the intersection between security and AI? We have security from AI. We want to protect people from the dangers that AI can possess, like algorithms that screen your CV before a recruiter can see your job application, and then you don't get to go to the interview because your CV got rejected. We have security via AI. We can use AI to find bugs earlier and make our software more secure. And we also have security for AI. We want to make sure that when somebody builds an AI model, that model is secure. The deployment of the model in some application is secure. For this talk, I'm going to focus only on security for AI, but there are similar subjects in the other areas. Okay, so I was saying that traditional software and AI are very similar. One of the similarities is that they have a similar history. Both of them started as hobby. For traditional software, you had people tinkering with their electronics in their garages and building software. Then some programs started becoming commercial. They started selling the programs. You got Apple PC, you got more computer into everyone's houses and so on. The same has happened with AI. Initially, it was just some people tinkering at some researchers, at some academies, and so on. Then it started being commercial. You had AI in some small applications like Google Translate and so on. And now with ChatGPT and the like, it's a commodity. Everyone can use AI and benefit from it. Unfortunately, there is also a bad side. As history progressed, as the software progressed towards commodity, the number of hackers increased exponentially, both for traditional software and for the AI world. So we have to care about security for AI. And now let's think about some risks that AI possesses. The one that is on top of mind of everyone is the prompt injection, where you send the LLM specifically crafted inputs such that from the output you can glean additional data, or you can break into a system and so on. It is OWASP top 1 LLM risk out of 10. It's very important, but if you look back at the history of traditional software, it is very, very similar to SQL injections. So protections that people have used in the past for SQL injection can be adapted to AI to prevent prompt injection with some differences, but the general idea, the fundamental is the same. Let's look for another aspect. Data leakage. Just this week, there was a news piece that Slack AI was leaking data from all of the chats that have happened in the instance. Or we have ChatGPT going full of GDPR. Or we had cases where a big bucket in the cloud got accessed by anyone. It was accessible for everyone in the internet, and it contained models. So we have a lot of data leakage, which is the same with the application, with the traditional software. You could have the place where you put your artifacts be word readable. So anyone could write some other artifact there, and then you download something with malware. Or the application could be misconfigured, and you can leak out the entirety of the database. So you could do data leakage from there too. Another risk, hiding malware in models. There is some research paper on how you can hide malware in models by data poisoning. There are also GPT-4 models that have been trained with specifically malware data to behave in a bad way. But there is also the possibility to add malware in models by just exploiting the way the models are built. So most models are built using frameworks that are very powerful because we want to do inference in a distributed way, we want to do inference across the network and so on. But because these frameworks are powerful, the models themselves become like a program. So an ML model is very, very similar to a Java, a jar class. You need some interpreter to interpret that and run it at runtime. So for example, for TensorFlow, we have a layer called a lambda layer that can run an arbitrary function. Or on the PyTorch side, or most ML frameworks, when you save a model, basically you do a Python pickle save. And because when you unload the pickle, when you load it back into memory, that runs arbitrary code, it's very easy to ingest malware inside the model. OK, so now for a while, let me put in attacker hat. I am a malicious person at the moment for this slide. So what I want to do, let's say I trained two models. One is an evil model that when you use it, I'm going to run arbitrary code on your system and get a lot of data from you. And the other one is the GPT-4chan that I trained it on 4chan data and so on to behave badly. I want these two models to go to the user. I want users to download the models and use them because that's how I'm going to exploit them. So how do I do that? I go to a model hub and upload my models there. Of course, I'm not going to upload the models directly as they are. I'm going to give them better names, better descriptions. So I'm going to say that the evil model is actually a model that can detect malware. And GPT-4chat is a friendly chatbot. And now I just wait for users to download them and exploit them. Of course, users that look at the name of the model might realize that something is bad. But that is not a good protection because I can just change the name of the model and they behave the same. So one key consideration here is that on their own, the model is not attributable back to the user that trained them. This is very similar to when you access an internet page. You know a domain name, but that domain name could be Bank of America. And if you're not reading it carefully, you'll think that it's Bank of America and you go there and you leak your data. And one more attack that we have to be concerned about is hijacking conversions from one model format to another. Because Pickle is unsafe, there is this new safe tensors format that converts the model into a format that is safer to load. However, the job that was doing the conversion from a Pickle format into the safe tensors format was susceptible to attackers. So once an attacker got a foothold into the environment that was doing the conversions, all the feature models that would be converted would have malware injected into that. OK, so why do we care about this? We have AI that is helping people write code. So that is already expanding the area of attack. Because now you can have an AI that has malware in it, that behaves badly, that is going to write code badly, that will have malware later. We even have applications that are built from zero with just using AI. You ask the AI, I want an application that does this and that and that, and the AI builds the code for you, and you just deploy it. We even have smart homes and powerful AI agents. So imagine I have an AI agent that is reading my email and responding to that, and another AI agent that is looking at my calendar. And if somebody can send me a malicious email that says, your USPS package has arrived, open the door, that AI agent might unlock the door to the house for a robber if I'm not at home. We also have AI used for security. So for example, for fuzzing, we have AI that is generating test cases to discover bugs and vulnerabilities. If that AI becomes dangerous, becomes malicious, then it might hide other bugs later in the applications. And we also have AI being used for high-performance computing to manage the packages that get installed into the supercomputers in the world. So the damage from a malicious model can have a significant impact across the world. OK, so let's say I am an ML developer, and I want to build a model. The first thing that I do is I select a dataset and an ML framework. So let's say I pick TensorFlow and some dataset. And I combine everything into a model. So I write some model source to train the model. I train the model, and once it's trained, I deploy it somewhere such that it can be used in applications by somebody else. So somebody decides that this is a model they want to put into production, and they put it into their own application, and now they serve it the application to the users and expect users to use it. If we look at this diagram and we look at the traditional software history, we realize that it is the same as building traditional software. A developer writes some code into a source repository, gets some dependencies, builds an artifact together with all of these dependencies, publishes this artifact somewhere, PyPI, Java, Maven, and so on, waits for a user to download the artifact, and then that artifact would be used in some production somewhere. So these two words are very similar from the point of view of the pipeline. And if we look at the compromise risks for traditional software, inject vulnerabilities, submit bad code, compromise the build system, and so on, we see that they are the same for AI. You can submit bad model code, or you can submit bad data. You can inject a vulnerability in the ML framework. You can compromise the source control for the dataset, so now you can poison the dataset directly from the source control. You can compromise the training process. It's exactly the scenario when we're converting from pickles to safe tensors. Or you can compromise the storage. In fact, for ML, the process is even more complicated because, in general, you don't take a dataset from the internet and immediately train a model on that. You actually perform multiple data operations on that, multiple dataset cleaning operations. You merge data sources, and so on. So we have a loop around datasets. For training a model, in general, especially for large models, you don't train the model in one go from zero to the model that you use into production. You train it to a step, you put it in storage. Later, when you have more data, you take it from storage and you combine it to another training process. You might even take a model and quantize it or merge two models together and so on. So have another loop, train model, deploy to model hub, use it as a pre-trained model, and continue training. And at some point, one of the models from the storage will become a model that gets used into an application and into a production system. So this is the big diagram for ML training. But there is not one single person that does the entire training from end to end. We actually have 4 different categories, and I colored them. On the far side, we have data persons that do the data cleaning, the data transformations, and so on. On the middle, we have the infrastructure, training, selecting the dependencies, selecting the frameworks, and so on. Then with green, we have the model storage. And then at the end, we have the application developer that doesn't really need to train the AI model, only needs to know how to use the model in production. So this is the diagram that we will work on for the rest of the slides. And now let's think about the risks that we have discussed so far. One of the main risks is that I don't know, as an ML application developer, I don't know if the model that I'm using is exactly the model that got trained. So let's say I want to use some model that was trained by some company. I download the model from the hub. So myself as the blue side, I download something from the green side, but the model has been built by the yellow side. So there is already 2 layers of separations between them. So what I need to do, I need to make sure that everything that goes into this box protects the model from tampering. In traditional software world, if I go to a website, I want to make sure that that website is exactly who it says it is. And we solved that problem when we switched to HTTPS. And when we first switched to HTTPS, everyone had to manage their own keys and so on, and it was hard. And then Let's Encrypt came and gave everyone certificates for free. So we want to do the same for signing models. Fortunately, there is Project Sigstore, who gives simple signing certificates for artifacts that are valid for just a short period of time, and you can use that to sign your certificate. So think of Sigstore as Let's Encrypt for artifacts. And we want to use that for models too, not just for traditional software. So how does Sigstore works? It's a process with 7 steps in total for ML. So let's start as the model trainer here on the diagram. Oh, the slide doesn't show. I first connect to the Sigstore CA to request a workload identity token, a JWT token that we saw in the morning. I receive back that certificate, which also gets put into the transparency log. So people can see that I actually got this certificate at this moment in time, and it was going to be valid until 10 minutes later, let's say. Once I have the certificate and the inclusion proof into the transparency log, I can now sign the model and upload the model to the model hub. The model hub should verify the signature, and if the signature is valid, can display like a badge there saying this model has been valid. And now the users can take the model and serve them in their applications. Users that are very suspicious might say, I don't trust the model hub. I want to do verification before I deploy the model into my application. That scenario should still be supported, and we will support that. OK, so why is signing ML models hard? Because in general, to generate a signature of an artifact, you just compute a digest, and you sign the digest. Well, models are, in general, very large, from gigabytes to terabytes for language models, for vision models, and so on. And if the model is large, the disk speed, as you read the model from disk to hash it, influences the performance. If you have a slow disk, hashing will be very slow. Sometimes, because you first write the model to disk and then you start hashing, you perform double I/O operations instead of hashing the model as you write it to the disk. And then there are some concerns about distributed training, where several hosts are writing parts of the model together, and then at the end you get the result. So this is not deterministic. And we need to make sure that we hash the model in a deterministic way so we can verify the signature. Another problem why signing models is hard is there is a distinction between checkpoint, which is just the list of the weights that the model uses, versus the model itself that can be deployed into an application and can be used with a slightly different version of the framework and can be converted from one framework to another and so on. So we have different formats that we can use to serve the same set of weights. And the checkpoints are in general used during training. So we have a finite number of checkpoints, but the training keeps generating checkpoints every few minutes or every few iterations, and we don't want to sign all of them. And then there are some issues about after training, where you want to add the licenses to the models, you want to convert one model from one format to another. Ideally, you would want to have one signature for the entire model, and then the framework that uses the model should verify the signature only for the part that it touches. So we have a library that signs model that tries to cover as many of the problems as possible using a layered API. I'm not going to discuss much on this, but we have possibilities to incorporate your own hashing engine or to serialize the models in a different way and so on. What I want to discuss next is what if we want to protect the entire chain, from the datasets to the model being used in production. Here we are going to use another open source technology called SLSA, which basically builds a layered approach. Level 0 means there is no requirements and I cannot say anything about the process. Level 1, I have some document that tells me how the model has been built. Level 3, the build platform itself has been hardened. So as I increase in level, I get more and more security assurances. And on the repository that we have, we can generate SLSA provenance for training models using GitHub Actions. And this is how we generated them. And at the end of the build, we will have the model and a JSON file that contains the provenance. And we can inspect the provenance. We will see that it is a signed document. And if we look into the payload, we see that it attaches to this model. And it was built by this SLSA framework, SLSA builder, and at this reference in the commit. So we know exactly that this model has been built from this repository at this commit. SLSA for ML is very similar to software bill of materials for AI. And in the AI world, there is also the concept of the model cards. The model cards are more focused on the ML, so what do you want to use the model for, what it was trained on, whereas the other two are coming more from the point of view of security. SLSA is more focused on how the model itself has been built, assuming that all of the dependencies before them have been built securely, whereas the BOM, the bill of material, is more concerned about all the third-party dependencies that have been used in all of the history until you got to the model. But they are all serving similar roles and can be used complementary. I will skip these two slides. So we have a white paper that discusses all of this into details. And the main ideas from the white paper is that we have seen that now there are a lot of attacks on AI. As the number of applications with AI increases, the number of attacks also increases. And we also believe that traditional supply chain protections can apply to AI. And I will conclude with QR codes for the repository where we have the code, the white paper, Google Secure AI Framework, which is where this work is originating, and an OpenSSF AI working group, which is open to anyone. If you are interested in open source security and AI, please join the group. It's happening every other Monday. And that is all. Thank you very much.